Welcome to today's paper reading. Today's paper is titled, Prover-Verifier Games Improve Legibility of LLM Outputs. This paper was published on the AR14 preprint by Hendrik Kirchner and colleagues from OpenAI. The abstract discusses the importance of legibility in the outputs of large language models, LLMs, particularly in the context of solving grade school math problems. It highlights that optimizing chain-of-thought solutions solely for correctness can reduce their legibility. To address this, the authors propose a training algorithm inspired by the Prover-Verifier Game, which involves iteratively training small verifiers, helpful provers, and sneaky provers. The results show improvements in the helpful prover's accuracy and the verifier's robustness to adversarial attacks. Additionally, the training enhances human accuracy in verifying solutions, suggesting that training for checkability by small verifiers is a practical method for increasing the legibility of LLM outputs to humans. As machine learning systems are increasingly applied in critical areas, the need to justify trust in their outputs becomes paramount. One way to build this trust is by ensuring that these systems can produce explanations that are understandable to humans. This concept is similar to how courts provide clear, written opinions to justify their decisions. In this paper, the focus is on making outputs from large language models, LLMs, more legible to humans. This is approached to optimizing model outputs for legibility via human feedback, which has its limitations. A complementary approach involves using larger LLM provers to generate chain-of-thought (COT) solutions that can be checked by smaller LLM verifiers, aiming to enhance legibility. The study also explores the concept of checkability, defined by completeness and soundness, inspired by probably approximately correct (PAC) verification and interactive proof systems. The proposed method involves an iterative algorithm, the Prover-Verifier Game (PVG), to train legible provers and robust verifiers. Figure 1 illustrates the trade-off between legibility and accuracy in solutions generated by large language models, LLMs. When solutions are optimized solely for correctness, they achieve high accuracy but are less legible to humans. In contrast, solutions initialized with human-written math derivations are more legible but less accurate. The proposed method, which involves checkability training, manages to retain high legibility while achieving an accuracy that falls between the initialization and the correctness-only baseline. This balance demonstrates a legibility tax, where improving one aspect, legibility, comes at the cost of the other, accuracy. Figure 2 showcases the results of checkability training, highlighting the production of legible and well-structured solutions. The figure presents 3 sample solutions generated by the helpful prover across different rounds of checkability training. These examples illustrate how the training process enhances the clarity and coherence of the solutions, making them more accessible and understandable for human evaluators. In the realm of computational complexity, our training setup closely resembles learning a verification protocol for NP problems, as initially explored by McAleese in 2000. By allowing more interactions, we can extend this setup to interactive proofs, as demonstrated by Babai in 1985 and more recently by Goldwasser et al. In 2019. Goldwasser et al. In 2021 and Utreya and Schaefer in 2023 applied interactive proofs to PAC verification, showing that a verifier can learn a hypothesis class with significantly less data through interactions with an untrusted prover. In contrast, our work assumes a capability constraint on the verifier, which cannot produce a solution independently even with infinite data. This approach was first connected to the alignment problem by Anil et al. In 2021, who showed that different game setups lead to different equilibria. Chen et al. In 2024 applied Prover-Verifier Games to interpretability in image classification, but unlike these works, our verifier's task is to judge the correctness of solutions rather than classify inputs. Amit et al. In 2024 trained LLM provers against a manually defined verifier, whereas our verifier is learned. We draw inspiration from these theoretical works and aim to empirically train for checkability on a non-trivial domain at scale. Figure 3 illustrates the legibility problem in AI-generated code. It shows how a superhumanly capable but poorly aligned AI might produce highly efficient code that sacrifices legibility for conciseness or performance. The example code is adapted from the Bytonic sorter, a method used for parallelized sorting of elements in a list, as documented by Wikipedia contributors in 2023. This figure highlights the trade-off between efficiency and readability in AI-generated code, emphasizing the need for balance in AI systems to ensure both functionality and human understanding. The setup begins with a formal definition of checkability, which involves two key properties, completeness and soundness. Completeness ensures that the prover always generates correct solutions, while soundness guarantees that no adversarial prover can fool the verifier. In practice, these properties are approximated due to the nature of neural networks. The Prover-Verifier Game is a two-player game where the verifier's utility is based on a negative classification loss, and the prover's reward is aligned with the role-assigned correctness. Training objectives for both the verifier and the prover are designed with specific loss and reward functions. The verifier uses a relative loss based on comparisons, and the prover employs proximal policy optimization, PPO, to maximize expected rewards. Different reward variants, such as signed relative convincingness, SRC, correctness-gated convincingness, CGC, and iterative Goodharting, are explored to prioritize various aspects of the prover's performance. In this section, we present the results of our study. First, we discuss the baseline approach, which involves training the prover model directly for correctness. This method achieves strong performance on grade school math problems but results in solutions that are longer and less legible, making them difficult for human contractors to evaluate. Next, we explore the dynamics of checkability training, where the helpful prover improves its convincingness, while the sneaky prover produces incorrect but convincing solutions. The robustness of the verifier varies with its size, with smaller verifiers being less stable. Finally, we examine the human legibility of the solutions. The verifier becomes more robust over time, the sneaky prover's flaws become more subtle, and the helpful prover's solutions improve in both correctness and legibility. Figure 4 illustrates the dynamics of model performance and human legibility during reinforcement learning training. Initially, the model accuracy shows a strong performance, peaking and then dropping at 8K steps due to reaching the maximum completion length. The mean accuracy of time-constrained human contractors evaluating solutions declines from the initialization to later training stages, indicating a decrease in human legibility. Additionally, the time required for contractors to correctly label solutions increases, highlighting the challenge faced by humans in assessing the increasingly complex solutions produced by the trained prover. The mean accuracy of contractors per solution is analyzed in relation to model accuracy, revealing a significant drop in human performance as model accuracy increases, particularly evident in the quartiles of model accuracy. This suggests that while the model becomes more accurate, its solutions become less legible to time-constrained human evaluators. Figure 5 illustrates the dynamics of the prover training phase across multiple rounds for a pair of verifier and prover. The figure shows the mean verifier score of correct, solid lines, and incorrect, dashed lines, solutions in part A, and the accuracy in part B, as a function of reinforcement learning, RL, training steps. The columns represent subsequent rounds of training, and the lines are color-coded for the helpful, red, and sneaky, brown, provers. An arrow indicates the increasing number of steps before the accuracy of the sneaky prover drops below 10%. The training is early stopped when sneaky incorrect solutions become as convincing as helpful correct solutions. Part C displays the average accuracy for the helpful, top, and sneaky, bottom, provers as a function of the completed fraction of each round. This verifier is 10-3 the size of the prover. Figure 6 illustrates the increase in verifier robustness against sneaky-only attacks, measured by the difficulty of these attacks and the balance best of n accuracy. The number of steps required for sneaky provers to find an exploit for SRC, Goodharting, and CGC adversaries is shown as a function of verifier sizes. An attack is considered successful for SRC and CGC adversaries when the sneaky prover becomes 95% incorrect, and the average verifier score of sneaky incorrect samples matches that of helpful correct samples. For Goodharting adversaries, success is declared when the prover's accuracy drops below 0.2. The figure also shows the fraction of correct solutions when selecting the most convincing out of n balanced samples for varying n in different rounds, using solutions from the last checkpoints of current round helpful provers. Figure 7 illustrates how flaws introduced by the sneaky prover become more localized and harder for time-limited humans to spot. Part A shows the mean and minimum validity scores over portions of correct and incorrect solutions from initialization and different rounds of checkability training. Part B presents the mean accuracy of time-constrained human contractors when evaluating solutions from the sneaky prover at various rounds of checkability training. Part C provides two examples of incorrect solutions with high verifier scores from different points of training, with flaws highlighted in red, including an incorrect translation of words into equations. Figure 8 illustrates the impact of checkability training on model performance and legibility. Panel A shows the mean accuracy of the helpful prover increasing over different rounds of checkability training. Panels B and C present the mean accuracy and time required for time-constrained human contractors to correctly label solutions from the helpful prover at various training rounds. These metrics indicate that as training progresses, the helpful prover solutions become both more accurate and more legible to human evaluators. The correctness-gated convincingness (CGC) reward prioritizes correctness and incorrectness over convincingness. This reward leads to worse training dynamics, with the sneaky prover reaching low accuracy and no human evaluation conducted. In contrast, the iterative Goodharting training involves the prover being trained with just the verifier score, which risks over-optimization. The training dynamics show that prover accuracy drops below 0.2, and verifier sizes from 10 to the power of -4 to 10 to the power of 0 affect robustness. Human judge accuracy remains stable across rounds, indicating potential issues with human legibility improvement. Figure 9 illustrates the training dynamics of the prover with the correctness-gated convincingness (CGC) reward across different rounds. The top part of the figure shows the average training verifier score, while the bottom part displays the training prover accuracy for both the helpful and sneaky provers. Notably, the verifier is significantly smaller than the prover in terms of pre-training compute. The figure highlights that the number of reinforcement learning steps required for sneaky incorrect provers to become as convincing as helpful correct provers decreases from round 1 to round 3 and then increases from round 3 to round 5. This suggests that the CGC reward leads to varying training dynamics, with the sneaky prover's accuracy decreasing rapidly and its convincingness rising more slowly compared to other rewards. Figure 10 illustrates the iterative Goodharting prover training dynamics across various verifier sizes ranging from 10-4 to 100. Notably, overoptimization is delayed in higher rounds, with some degradation observed for a verifier size of 10-3. Larger verifiers demonstrate better maximum prover accuracy and achieve improved robustness more quickly. Medium-sized verifiers, specifically those in the range of 3 × 10⁻³ to 10⁻², benefit the most from this iterative Goodharting training approach. In this discussion, we address several limitations of our study. Firstly, we focus on domains that allow natural language justifications, particularly the math domain. This is because natural language explanations are common and necessary for building trust in mathematical conclusions. However, in domains like facial recognition, it is challenging to provide such explanations. Secondly, our setup requires ground truth answers, which is feasible in the math domain but may not be in others where collecting ground truth is difficult or costly. We suggest that out-of-distribution generalization could be a solution, though it was not studied in this paper. Thirdly, by training the chain of thought to be legible, we may have limited the prover's accuracy. A better approach could involve training a separate model to convert the chain of thought into a legible justification. Additionally, our study was limited to one dataset, which is relatively easy and standardized. Future work should extend to harder datasets and fuzzier domains. Lastly, our prover initialization and heterogeneous experiment setups introduce further limitations, which we discuss in detail. In this section, the authors acknowledge several individuals and teams for their contributions. Jeff Wu provided valuable technical insights and discussions. Boaz Barak, Jeff Wu, Jenny Nidishinskaya, and John Schulman offered helpful feedback on earlier drafts of the paper. The platform team was thanked for their infrastructure support. Additionally, Matty Roy, Spencer Pape, and all contractors involved in the human data collection effort were acknowledged for their contributions. Thank you for watching.